questions here? Guys, this is the first session, so you're free, more than free to ask your questions. We'll try to go through as many as we can, just so you guys have a lot of opportunities to ask as many questions as possible. So don't feel free to stop me at any time if you're not following. Right, so let's look at the next problem. It's asking us to sketch the region that is enclosed between the curves y is equal to the absolute value of 2x minus 3 and y is equal to negative x plus 3. So we have an absolute value function again, meaning we have to define it piecewise, right? So two cases. When x is greater than or equal to 3/2, and when x is less than 3/2, right? So at this point, I'm assuming that you guys remember how to define piecewise functions. So that's why I'm not going to go too in depth into that. Right. So for the case where x is greater than 3/2, we have that the function is positive, which means that it's equal to 2x minus 3. Can you please meet? Yeah, right. So that is if x is greater than or equal to 3/2. And if x is less than 3/2, we have the opposite, which is negative 2 plus 3. That is if x is less than 3/2. Right, so now that we have that, we can try to sketch that onto our axis. Right, so now we have the case where x is equal to x is less than 3/2 and x is greater than 3/2. So 1, 2, 3. So 3/2 is somewhere here, 1.5. So please meet yourselves. Right. So now that we have that, we can see that for the values of x less than 3/2, we have our function equal to negative 2x plus 3. So if you take a value less than 3/2, for example, 1, you get that when x is equal to 1, the function is equal to 1, right? So 1 somewhere here. So that means that the function on the left side looks something like that. And then on the right hand side, for value greater than 3/2, let's say 2, for example, when x is equal to 2, the function is also equal to 1. So on the right hand side, we also have something like that. And now for a second curve, which is y is equal to 3 minus x, right? So let's first write down here that on this side we have 2x minus 3. On that side, we have, right, so we put it there. Oh, on that side, we have y is equal to negative 2x plus 3. So for a second curve, y is equal to, when x is equal to 0, we have y is equal to 3. So 2, 3 somewhere. And when x is equal to 3, y is equal to 0. So there. So our second function is looking at that like that. And that is y is equal to 3 minus x. And we have now the enclosed region, which will represent in red here. And we are asked to find the points of integration. So, oh, sorry, not integration, but interception. Point of interception. So these are the 2 points of interception. So the first point of interception is between y is equal to 3 minus x and negative 2x plus 3. So when 3 minus x is equal to negative 2x plus 3, x is equal to what? The 3 cancels, obviously. You're left with x being equal to 0 then. Right, so that means that the way we sketched it right here is a bit off. So, all right, so this should be there, but then the intersection point should be somewhere there. Right. So now that that's fixed, that's our first point of intersection. So the second point of intersection is now when 3 minus x and 2x minus 3 meet. And in that case, x is equal to 6 over 3, which is 2, right? So the intersection is 2 here. And our second intersection. So that would be our solution for sub-question A. Now, sub-question B is asking us to find the area of this region, which we'll have to divide into 2 again. Right? And those 2 can be evaluated as a total integral. So let's first, the first section will be from 0 to 3 over 2. Right? And in that case, we have that 3 minus x is greater than negative 2 over negative 2x plus 3, which becomes plus 2x minus 3 dx, plus the second part, which is the integral from 3 over 2 up to the second point of integration, which is 2, where we have 3 minus x greater than 2x minus 3, which is negative 2x plus 3. Evaluated. And when you do that, you find for the first integral, 3x, no, let's put it here, 3x minus x squared over 2 plus x squared minus 3x evaluated between 0 and 3 over 2 plus 3x minus x squared over 2 minus x squared plus 3x evaluated between 3 over 2 and 2. When you plug in the higher limit, we have 9 over 2 minus 9 over 8 plus 9 over 4 minus 9 over 2 minus 0. right? Plus 6 minus 2 minus 4 plus 6 minus 9/2 plus 9/8 plus 9/4 minus 9/2. Right, so please double check the calculation to make sure I did not make a mistake somewhere. So that's that. And then simplifying this now, 9/2 here and the 9/2 there cancel. The -2 and -4 cancel with the 6. What else? 9/8 and the 9/8 there. Right, so then we're left with the 6 plus 9/4 plus 9/4 again minus 2 times 9/2, which is just 9. That will give us 9/2 minus 3, which is equal to 3/2. Just double check that calculation as well, but it should make sense. Any questions on this particular example? All right, let's move on then to question number 4, where we are looking at the volume now. So, right, so we are asked to find the volume, right, of the solid whose base is the region that is between the curve y is equal to the square root of x and the x-axis from x is equal to 0 to x is equal to 4, and that region is rotated, right, about the x-axis, right? So that would be our A. So let's try to represent that graphically. So we have graphically x-axis, y-axis. So the curve y is equal to the square root of x is a curve that looks like this, right? Something like that. So the region that we're looking at is between this curve and we told the x-axis, and that is the x-axis, right? And we are asked to find this between x is equal to 0, which is the origin, and x is equal to 4. So this is 1, 2, 3, 4. So x is equal to 4 is that straight line. So basically we are asked to find the volume of when this area here is rotated about the x-axis. So if you think about it, this is the x-axis. So when you rotate this, right, about it, you'd have a reflection of that curve on the negative side as well. And wait, sorry. Let's just do this up to there and do this up to there. And then as soon when you rotate it, it turns into some sort of a cone looking shape, right? So that would be something like this, right? If you think about it, right? When you rotate it about the x-axis, right? And you can clearly see that as you rotate it, this area here will start forming a cone-looking shape around the x-axis, right? So now when you do that, now you get a volume. Before you had an area of 2 dimensions, now you have a volume with 3 dimensions, right? So using the cylindrical shell method, right, we know that for a case where you are rotating about the x-axis, the volume, right, so let me just write it down. So using the shell method, you have that the volume of that solid, right, when it's rotated about the x-axis is given to us as 2 pi multiplied by the integral from a to b of y multiplied by x of y, right? So your function must be x of y dy. So now we are given that our function is equal to y is equal to x. That just means that x is equal to y squared, right? So if you go back to our formula here, we have this is equal to 2 pi. And obviously we're doing in terms of y because we have dy there. So you have to look at the change in y between x is equal to 0 and x is equal to 4. Right? And the way you do that is you just substitute the values of x into the original function. So when x is equal to 0, y is equal to 0. When x is equal to 2, y is equal to, sorry, x is equal to 4, y is equal to 2. So those are the boundaries. The integral of y multiplied by x of y, which is now y squared, dy. So this then gives us, right, 2 pi multiplied by the integral from 0 to 2 of y cubed dy, which is just 2 pi multiplied by y to the 4 over 4, evaluated between 0 and 2, which gives us 2 pi multiplied by 2 to the 4, which is 16 divided by 4, minus 0, which is should be 8 pi, right? So that is the volume of that solid. But now the question is also asking us to try repeating this calculation for the case when the enclosed region, which is the same region, is now rotated about the y-axis. So let's try to represent that graphically. So if you try to represent this graphically, we have the same region. same region. Let's paint the red. So this same region here, but now it's rotated about the y-axis. Right, so when it's rotated about the y-axis, again, you have to sort of visualize it mentally. It would be so again, this is just a representation, right? So bear with me. It would be something right? Something looking like don't know if you guys can see it visually, but basically so this would be the invisible side, right? But if you rotate it, you really have to sort of think about it in your head, really, because this is a 2D paper, so I can't really represent a 3D object on that. I'm just basically just representing sort of a projection of what it would look like. But basically, if you think about it, it would look sort of, let me see. Let me see. Right, okay, I have a better way of representing this. Right, let me try to represent this in a better way, just so you guys can see what I mean. So you would get something that looks like right. I think this is a little bit closer to what you would get, right? And obviously these are between the boundaries of, right, so you have to do this all the way there, all the way there. So this would be represented in such a way, right? Between, and this would be -4. Right, so that's how you should sort of think about it, which gives us like a cone looking shape, right? And in that case, our formula now, right? So our formula will be V is equal to 2 pi from now C to D of X, right? Multiplied by Y as a function of X, right? dx. That is when you're rotating about the y-axis, right? So in that case, we need to know that we are integrating in terms of x, and we already have the values for the for the volume in terms of x, right? So that would be from 0 to 4 x multiplied by y of f of x, which is the square root of x, right? So square root of x dx, which will give us 2 pi multiplied by the integral from 0 to 4 of x to the 3 over 2, if I'm not mistaken, dx. And that is just 2 pi multiplied by x to the 5 over 2 divided by 5 over 2, evaluated between 0 and 4, which is 2 pi multiplied by 4 to the 5 over 2 divided by 5 over 2 minus 0, which is equal to 2 pi, right, multiplied by 2 to the 5 divided by 5 over 2, which will just be the same as multiplying by 2 over 5, which is equal to 2 to the 7 over 5 pi, right? And obviously you can evaluate this further, right? So any questions at this point? It would be more helpful for everyone if you attempted these problems on your own, so you can sort of understand what I mean. Right. Okay. So that is done. Now let's move on. The next problem is now asking us to find the volume of the solid, right? The solid obtained by rotating, right? So rotating the sine function between x is equal to 0 and x is equal to pi about the y-axis, right? So let's set it up graphically. So we have our axis as such, and here we have 0, and somewhere here we have pi, and obviously you guys know that the sine function is concave down between 0 and pi. So it would look something like that, and that is a function y is equal to sine x, and we are asked to rotate it about the x-axis. And when you do that, so this region here is what's being rotated. When you do that, you would have something that looks let me see if I can represent it any better. So you would have something that looks a little bit like bear with me. So you would have something that looks like that. Something like that. So basically it would be like I said, it's difficult to represent it in a 3D space, but it would look something like that. but you could try to imagine it in your mind as well. So maybe that makes a little bit more sense if you try to imagine it that way, rather than me trying to represent it graphically on a 2D paper. So it would be something like that. Right. So anyways, the formula now for this volume is 2 pi, right? Once again, now we have from 0 to pi, those are our limits, 0 to pi, x, right, multiplied by y of x, which is sine, x multiplied by sine of x, dx, and we are asked to evaluate this, and that is where we would use our use substitution, right? And I think that's where we'll continue tomorrow, because we go into use substitution, which is basically the topic of the next couple of questions. So I think that's what we'll mainly focus on tomorrow. We'll focus on finishing this one and then moving on to more questions that tackle integrals using use substitution. Right, so thank you for joining. Please attempt. You can always attempt it and continue in anticipation of what we'll be doing tomorrow. But yeah, I think that's where I'll end because we're running out of time as well. So hopefully the session was helpful. Do you have any questions? I'll stop recording now, and then if you have questions, you can always ask them.